Hi, this is a extra demo from the scalability team where we're going to look at proof of concept for how to make Git clone faster. And I should start by sharing my screen. And I hope it is readable. So yeah, about Git clone. So just what happens during, I'm going to do a Git clone on my GTK, and I'm going to tell you a little bit about what happens because you need to understand the different pieces, and I want to give this context. So this is an SSH clone. Now, first, what you see is that the server is preparing the clone for us, and this takes time. And it's giving us this progress information. And as the client, we're just waiting and doing nothing right now. So the server is still thinking about what to send us. And now it's compressing things that it wants to send us. And now it's starting to copy data to us. And at this point, the client is actually analyzing the data that the server sent. So this always has to happen, this receiving objects part. You can't skip that. But everything that happened up till here was just us waiting for the server. Now let's wait for this to complete. Now the client is doing some more analyzing of the data. So this has nothing to do with the server. We can't make this faster. And this is a big clone because it's 900 megabytes. That's a lot. And now it's done. Now it's cloned the repo. So the cool thing is, and I really hope that the demo works now, is that I'm going to do it again. And now it jumped immediately to receiving and analyzing the data, and it skipped all the work on the server. Because it cached the work that the server has to do.
Cached by? Like, what's the key?
The key is a number of things, but it's mainly the objects that the user wants. And if we're really lucky, I'm not super sure, but I think this cache entry even works for HTTP. Let's try. Now do an HTTP clone. And yes, so it wants the same objects and it's still in the cache and it's sending us that to us now. Now this is a full clone, and that's not the only thing you might do, but it works the same for a shallow clone because that is just a different list of objects that the client wants. Let me just show. No, I can Control C this. I can make it as a shallow clone. It will be faster because it's less data. The first time it has to compute the data. That took a few seconds, and now it's sending the data. And now the second time, it doesn't have to compute the data, it just sends it. So that is one thing that is cool. Another thing that is cool is that, okay, I think this, sorry, I don't want to get ahead of myself. This is one thing I'm excited about. Another thing that's exciting is what if happens if you do two clones at the same time? Now for this, I use a special testing tool that's in the GitLab repo. Because when you do a proper clone, the client has to analyze all the data that gets sent by the server, and that is important, but it uses a lot of CPU. And if you want to do a bunch of clones in parallel, then my laptop becomes the bottleneck because it needs to analyze all the data that gets sent to it. And this analysis tool doesn't analyze the data, it just throws it away as fast as it can. So it only tests how fast the server can send data to us. And I think if I run it in here, it sends a slightly different request, so it's not cached. But what is fun is that if I run it in this other window, see this one on the left here is taking a long time because the server is thinking about what to send. Still thinking, okay, getting there. Okay, now I started the one on the right, and it immediately catches up with the one on the left. So what happens here is that when two requests come in that want the same thing, is that there's coordination, and we only create one process that fills the cache, and then both of those requests wait for the cache to be filled. And as it gets filled, they start sending the response. So that is sometimes called duplicate suppression, I think. So, and this is precisely what we want in CI, because in CI, you would have 100 jobs that are all cloning the same thing, and they would all have on the same GitLab server, and then that would let all of them wait while it builds the cache response, and then it can fan that out to all of them.
To show that, would it also be possible to demo that with those two? So like we waited to run the second instance of the
Yeah, sure.
analysis script, like until the first one had finished caching. But like if we started them both while the caching was still happening.
I need to clear the cache now, because the script will keep sending the same requests, and the cache is local to the GitLab process. So if I start GitLab, restart GitLab, then the cache data is still in the object storage. Well, it's local files right now, but it would be object storage. Actually, I can run it with object storage, but then it becomes embarrassingly slow because of my internet connection. By restarting GitLab, it's forgotten the cache data, but it's still in the storage. So you need a separate process that deletes it for you. That would be lifecycle rules on an object storage bucket. So the cache is now empty, and in both of these windows, I can just come to press enter very fast, and then we can look at the activity monitor, and you see that there's one Git process here that's using 100% CPU. So that's the server preparing the clone.
And so it's doing this for both of those requests.
Yeah.
With just one process. Yeah.
Yeah. What happens is that, now you can see both of them moving at the same time. I don't know if it's easy. Maybe they're too far apart. I should have put them next to each other, but you can see that they're moving pretty much in lockstep. And now GitLab is working very hard. And my understanding is that that is just what happens when it needs to copy a lot of data around. You can also see that Workhorse is working hard, which is kind of, I could tell you, your Workhorse is not doing something interesting right now. And that was it. So what happens is that, okay, I've shown you the thing. Do you want me to show you anything else, or shall I start explaining what happens on the inside? Or do you have questions?
I have a question.
Go ahead, Rachel.
So you said there the runners clone the same thing multiple times. Why is that?
Because of parallelization in the CI jobs. We have so many tests in the GitLab repo that if we would run them sequentially on one runner, that would take a very long time. So we split them, and we split all the tests over multiple machines, but they all run for the same merge request that's at the same commit. So they're all cloning that merge request at that commit.
Do you know off the top of your head how many clones are then done for each one? Are we talking in the tens or the hundreds?
It depends on the shape of the CI pipeline. So that could be it could be 100. This is the topic that started me thinking about this, because we have a sort of custom caching scheme specifically for the GitLab Rails project, where we try to avoid putting too much pressure on the GitLab server when too many of these CI jobs start cloning at the same time. And last week or the week before, that broke, and then that GitLab server had an incident.
Right. Okay.
Yeah, and this is a general thing that is not just on GitLab.com, but that we also hear from larger self-managed installations, is that if people have a massive CI system, and if you have a large project, that often happens, or if a project lives for a long time, then you just get more and more tests. And CI clones are one of the best ways, or the most common ways, I think, to knock over a GitLab server.
Thank you.
So for the GitLab Rails project, we have 116 jobs runs on a master pipeline. That will be different on a merge request pipeline, because a merge request pipeline might skip. So like if you just make a documentation change, it'll run like 6 jobs or whatever it is, but just the documentation linting and stuff. But in general, like we have over 100 jobs for our pipelines. That's a large pipeline, but I'm sure some of our customers have pipelines with more jobs. So yeah, it's a pretty common problem, I guess.
Yeah. And what's nice about this way of solving is, and this is, so what I wanted to show you on Friday was something where I was trying to make the problem tractable by only solving it for CI, for a small subset of the CI problem space. And I thought maybe if we just make the problem smaller and change the rules of the game, we can build something. And that worked. But then I started thinking about, it would be nice to solve the general problem and just make all clones cacheable. And we spent time investigating that in the past in the GitLab team. So I still had things about that in the back of my head, but at the time we didn't get around to it because it just seemed very complicated and we had other things to do that were more pressing. And there were also pieces of the puzzle that I didn't quite know how to solve straightforwardly. And because of the stuff I did late last week, I was thinking about some of those puzzle pieces in a different context, and then they seemed easier. So now I was able to revisit this. Well, yeah, think about it some more, and then I realized, wait, this one thing is the last piece of the puzzle I don't know how to solve, but I do know how to solve it now. So let's try that.
So this is just like completely transparent now, right? Like we don't need to, so what we were talking about before was like we have a CI pre-clone script that's specific to the GitLab Rails project.
Yeah, no,
what if we made something like that the default for all GitLab CI projects, and then you can override it if you want to? But now we're saying you don't need a pre-clone script because cloning will just automatically be cached.
Yeah.
And it doesn't matter if they're SSH or HTTP.
No.
Yeah.
And we even saw, which I was very glad that it worked, that you can have an SSH clone and an HTTP clone that asks for the exact same thing, and one of them fills the cache and the other one finds that entry from the other.
So can we, is it okay now an okay time to start going into the details of like,
sure.
So is it based on the ref spec that the client's requesting, or?
So how does this work? Well, so I have a merge request for this that I pushed earlier today.
Okay, cool.
And it's, maybe I can talk you through that first, and then we can talk about how it works. So it's a GitLab merge request. It's so this is hidden inside GitLab, and it adds a dependency to GitLab, namely object storage, to store these things, because they can be pretty large. If you do a full clone of the GitLab repo, that's 1 gigabyte. So you need very elastic storage for your cache. And I think object storage is the most practical, and it's basically auto-scaling for storage, which is exactly what we would need if we wanted to do this on gitlab.com. You could otherwise write all these large things on the disk, but then you need to provision your disk so that you know. It's really hard to do the calculation, I think. You need to know what size
Especially
the repos
because
are.
It would need to be per GitLab server, right? Like,
yeah,
you know.
and you need, and it completely depends on user behavior. And users can do bad things that put a lot of data in the cache. So one of the problems with this thing is also that the cache needs to have a very short expiry time, because otherwise you get a very high storage bill. Because this is very lopsided. Well, it's caching, which means that somebody reads something and you write it. And usually reading is cheaper than writing, but we're voluntarily writing all this stuff that the client just wants to read. So we're doing a massive amount of writing. So we need to make that as cheap as possible. We need to store that as short as possible. Yeah, so to try and talk you through how this works, under the hood somewhere, so Git has plumbing commands, right? So you have things, Git often hands off pieces of its job to subcommands of Git. And when you do a clone or a fetch, the main part of the work is building the pack file, which is the response, which is the packed Git objects. And there is a process that is whose job is to do that, and that is called Git pack objects. So we're caching at the level of Git pack objects. Now, the funny thing is that there is a configuration option in Git where you can say, instead of running Git pack objects with certain arguments, please run this executable and give it the arguments you would give to Git pack objects. So it's like a hook where we can see what Git wants to say to Git pack objects, but we can sit in the middle and do something different with it. And that's what this uses. And one of the reasons this was easier to implement is that we moved the Git hooks of that used to be in Ruby and in GitLab Shell, and they're now all integrated into Gitly. And what happens with these hooks is that they actually make a gRPC call back into Gitly. So we have a nested gRPC call. So the clone comes in, we start a Git process called upload back, and upload back wants to generate the back file, so it calls back objects. And then back objects starts our hook executable, and our hook executable makes a Gitly call back to Gitly. And then Gitly can run back objects, the real back objects, and generate the response. But because Gitly is in the middle, and because all these clones ultimately make calls back into Gitly, we can coordinate inside Gitly. And we can just coordinate in memory. And that is what makes this tractable. Are you still with me? The problem with caching, especially with caching like this, is coordination, right? If you make a naive cache, then you can just have multiple things filling the cache if they don't find something, and then you throw away duplicates. And especially with these clones, that is not what you want because it's very expensive. So you need coordination that if multiple things want to access the same cache entry at the same time, they coordinate and they wait for each other. And the coordination happens inside the Gitly process in memory. And that's also why by restarting the Gitly process, the cache was gone, because it's only remembering that these entries exist in memory. And because I think that's okay, because this is meant to be a short-lived cache, so it should be okay if you have a restart. But that's one of the questions to ask about this.
When you say short-lived, how long do you think it should live?
30 minutes, 15 minutes, I don't know.
Is there a way, and maybe you'll get into this into the merge request. So I saw in the issue we had in the scalability tracker, someone from a customer was commenting about what they do, but also what I think Microsoft do for large repos, which is to have sort of these incremental pack files. So you never repack the whole thing, but you just sort of have a series of like, this builds on this, builds on this. That currently isn't possible with this implementation, right? Like each like if I request a clone now, and that's cached, that's fine. If I request a clone now and
it has one new commit, then we create the
branch
whole
I'm
new thing
requesting
again.
is one new commit ahead. Yes, exactly.
Yeah.
That's start from
yeah.
scratch.
No,
but for CI, that's not a problem, because like CI is always, I want the magic pipeline ref to clone like for what I'm running, because that's how CI works. So that part's fine. Yeah.
Yeah. That other thing is another way of caching, and I think it's very hard to do that without changing the Git protocol, because the Git protocol assumes that you create one pack file that has all the data, and Git gets mad if an object occurs more than once in the pack file. So if you're trying to do something incremental and you accidentally add the same object twice, it blows up on the client. That's actually what I know pack objects hook from, because I tried building that and I thought, whoa, this works, this is awesome. And then I tried it some more, and then I hit the case where I included the same commit twice and it blew up. And then I spent a couple of days looking at why this happens and what I can do about it. And I realized that it's too hard, and I gave up. So if you want to do that, and that is of course a very valid idea, you need to communicate to the Git client that there are multiple pack files, and then it can download each of them, and each of them will have only one entry for each object. But you cannot just take multiple pack files, glue them together, and pretend it was one pack file all along, because then you can have duplicate objects and it gets rejected. And another reason why you might want to do that is if you have really, really, really large repos, which I know from presentations that Microsoft gave, that's a problem they have. Like the Windows repo is so large, they had to create a virtual file system that transparently fetches new Git data for you while you browse the directory on disk, just to make that manageable. And at that scale, you need this sort of thing. And so what I'm showing here will not work for that scale, because for that scale, you have a separate problem. Like you cannot do a regular clone anyway. So this only makes sense if your Gitly server can serve the normal clone, if your repo isn't that huge, but you just don't want to do it in parallel.
Yep. Okay. Thanks. I just wanted to understand how that comment related to this.
Thanks. Yeah, good question. So yeah, that is sort of the even bigger problem, and that needs changes in the Git protocol, and people are working on that. People at Google want this, people at Microsoft want this, and so the Git maintainers are somehow trying to come up with a way to make that happen, but that needs the protocol to evolve. So just to show a little bit more about how this thing works, I explained that all the work is done by back objects, that there's a hook in Git that allows us to sit in the middle and change things, and that we can coordinate inside Gitly. So in this merge request is the code that I was just showing, and I put all the magic code in one file, which I have here, which is 500 lines now, and it doesn't have tests, so it would be, and it's yeah, it is kind of subtle. So this is not a trivial feature, although maybe I made it too complicated, but well, make of it what you will. It's 500 lines without tests, and it hasn't been reviewed. And it seems to work. So what it does is, well, it has a global variable for the cache, and what you saw in the demo was that I was caching in my TMP directory. But this uses a library called Go Cloud Development Kit, which has an abstraction around Google Cloud Storage, Amazon S3, and Azure. So once you write an integration for this library, you can store on any of those things. So this code should just work exactly the same way, and it does on Google Cloud. I tried that, except it's slow because my internet connection to Google Cloud isn't fast enough. But that is a nice that's a nice library that also made this easier to look at. So this is an RPC that accepts the request, and here's something interesting. So here it computes the key that has to do also with Bob's question. So the inputs for the key are the path to the repository, the arguments for Git back objects, because those determine like if it's a shallow clone or not. So well, I'm basically taking anything that might change the outcome, and the arguments of the command are one thing, and the data on standard in, which is the list of commits that the user wants. And inside that key function, let me look for it for a moment, because I'm also including a cache ID that is scoped to the cache. So that means that if you restart the Gitly process, you're not going to find blobs in object storage that were created by a different process, even if they are for the same repo and the same request and the same data. And that is because there's some non-determinism in how the blobs are shaped. So you don't want to mix up blobs from two different caches. So it's like the process ID. Not literally the process ID, but I make sure that even if you restart the process, this is why restarting the process clears the cache, because this ID changes every time you start up. So that's how the key is made. And then we have a key, and then we try to get an entry from the cache. And if there isn't one, then we create an entry and we launch a go routine that will fill the cache entry for us. And then we go into a loop where we wait with a condition variable for IO to happen, or for the thing to be done. And every time we're woken up, we send whatever IO is there on standard error, we send whatever IO is in standard out, and we go back in. So this is the waiting loop. So none of these things that come in do any actual work. They just hand the work off to that go routine if they have to, and then they go into this waiting loop. And then there is that go routine. What does that do? Well, it runs the back objects commands, and it writes into a special kind of buffer. So I created a memory buffer for standard error and what I call the blob buffer for standard out. Standard error has the progress information, and it's important that the progress information gets delivered fast. And if you make a round trip to object storage, that gets we need to write very small blobs, and it gets very inefficient. So that is just done in memory. The progress information is in memory, isn't kept there for as long as this entry is in the cache. And then this blob buffer, reads a chunk of data, and the chunk size is, where is that? That is right now 50 megabytes. It should be not too small, because then you have overhead of creating lots of blobs, and not too large, because then you make people wait too long for their first byte. And that thing creates chunks in object storage, and once one of those chunks is finalized, it wakes up all the clients, and then they see, oh, I can send a new chunk to the client. So what it really happens is that we upload 50 megabytes of pack data to object storage, we finish it, and then we use the condition variable to tell the people who are waiting for it, here's a new chunk, and then they send that. And we also check if everybody went away, and then we stop, because otherwise people could trivially cause us to store a lot of data in object storage and waste a lot of CPU. And I don't know if it doesn't make sense for me to go through all this notification or all this code. I think, unless there's something you want to see.
It wasn't quite clear to me how you keep track of people waiting for, like I saw you keep track of the number of consumers, but I didn't quite follow that.
So number of consumers gets incremented when we create an entry or when we get an entry, and gets decremented by this. So it's just a reference count. And if we look for that function, yeah, it just does a reference count. But here we have, this is how we check it. So if this has all consumers gone, this returns true if it's 0. And then if we're in the write function of, say, the memory buffer, then it checks, are all consumers gone? Okay, let's just return early with an error. Does that answer your question?
Yeah, that's the part I was missing.
Yeah. I can go into more detail about what's happening, and I actually want to change this slightly, but I'm not going to, because the point is clear enough.
Why is the per process element to the cache key?
Yeah, good question. It's well, it doesn't matter for standard error, because standard error is in memory anyway. Actually, that's one of the reasons. So standard error is in memory. So if you would come back, you've lost your progress data. And maybe that's okay. You can send the pack data and without the progress data, but that's already less nice. And the other reason is that if you look at the blob buffer, right now it just checks if the current chunk is bigger than the maximum. But that means it won't literally be 50 megabytes. It will be any number over 50 megabytes. And exactly how much that is may depend on things outside of our control. So the boundaries between these blobs might be different. So we definitely don't want to mix things that are part of the, that have the same inputs, but are generated by different back objects processes. And if we want to keep them longer than, well, the other problem is then you would need coordination between processes. I think maybe that's the real answer. Coordination between processes is much harder, and then we would need something like Redis or something that lives outside GitLab and that survives the GitLab process, or that persists, or something that persists state beyond the GitLab process. And right now we have two kinds of state. We have in-memory states and we have object storage state. And if we would want to have the cache survive process restart, we would have to persist that in-memory state somewhere.
How many GitLab processes are we running? Like if we think about clones that happen from CI and we do the 100 something from GitLab or GitLab.
Well, they all go into one. Well, actually, it depends on if we're running prefect or not. I think prefect may have read balancing. I think that their GitLab team is working on that. I don't know how far that is. But
yeah,
most GitLab.com repos are not on prefect. And in that case, all clones hit the same GitLab process.
So as long as we're not distributing reads yet, this will be fine.
Yeah, if we're distributing reads, then we probably need something to put what's now in memory state that needs to live somewhere else, that is accessible by all those processes that serve the same repo.
Yeah, and I guess there are also cases where sometimes Git pack objects will contain something that we could say this is going to be the same no matter which process picks it up, but we can't, like, so for instance, if it points to a specific revision by SHA, like that's fine, like, but if it points to a reference,
It
then
never points
we
to a
can't.
ref. Refs get resolved before it gets back objects.
Okay, so then it should, well, because I'm just reading the commit that added this hook and it says with an asterisk. Pack objects is a pure function, like its output is a pure function of its input. So it seems like, yeah, if it wasn't for the progress stuff, we should be able to do that.
Yeah, it's another thing. Yeah, I mean, the short answer is yes, we should be able to do that. It just seemed to make things more complicated that I wanted to cut whatever corners I could
Oh yeah, for
to
sure.
get the
Like,
thing ready. And one of the problems I have is also how do you handle processes going away, or consumers going away, or the producer going away. And in the case of a Gitly process, they're either all there or the whole process is gone.
Right.
So you, if the moment, I mean, there still are distributed systems type challenges, but you have a more reliable, I think what I'm saying is you have a more reliable communication channel once, as long as you're inside the process, because the moment you're, I mean, you can do lots of things just storing state in Redis, right? That's actually what I was doing in the previous iteration, because then I tried to make workhorse processes coordinate and build a cache. So that I had to do in Redis. But then you have to, like, it becomes more difficult to notice if all the consumers have gone away, because a consumer, like, what does a consumer then have to do? It has to update a heartbeat or something in Redis to know that you know that it's there, and then you need to check those heartbeats.
And then you're already,
yeah.
you're
No, it can be. I'm sure it can be done, but it would be more challenging than what we're looking at here.
No, for sure. And like, you know, I think the reason we're asking this question is because, like, we don't know how often Gitly processes go away. Well, I don't know how often Gitly processes go away in general.
Well,
yeah, exactly.
When there is a deploy, but we don't deploy like, well, I suppose it depends on how often we make we merge commits to Gitly master, because after that they probably get deployed. But the other thing to consider is that we want this to be a short-lived cache anyway.
Yep.
So the amount of data we lose by restarting Gitly is also bounded by that.
Well, yeah, and also, you know, sorry, actually, let me just check something. So this is slightly slower, but it shouldn't be much slower, because you should be using the object storage that's related to wherever you're hosting your Gitly, right? So like, if your Gitly is running on Google Cloud, you should probably be using Google Cloud storage. If your Gitly is running on AWS, you should be using S3.
Also because
if your
of metering of bandwidth.
Yeah.
Because
if your Gitly is running on your own infrastructure, you should be using Minio on your own infrastructure, et cetera, et cetera. Because I was just thinking that overhead is the only thing that makes this, that's the only overhead with this, right? Like, realistically, like, there's obviously the bookkeeping overhead here, but I don't think that amounts to much. The only potential
the IO overhead is going
overhead.
the IO overhead is going to be an order of magnitude worse than the bookkeeping overhead.
Yeah, exactly. Because we have to upload it to object storage and then fetch
download it
from
again.
Object storage. Yeah, exactly.
Yeah, no, that is overhead for sure. And I think that's one of the open questions. Like, when you put all this together and you put it in production in real life, how bad is that overhead? And the other question in my mind is, how much data are we throwing in there? And is this can we write that much data, or how expensive is it to clone or to cache all this stuff? And can we upload that much data fast
and we
enough?
Can we, I don't know much about the arguments to get pack objects. Can we opt into this from the client side, or would it more have to be like,
thanks.
we'd have to say this repo is?
This is a very good question. How does this all happen? And if we look at Smart HTTP, that's for Git HTTP. Here we go. We're adding a Git config option as a flag to the Git upload back process. So at this point, we can check a feature flag and do it or not do it, first of all.
But we could also, yes. Okay, I see. Yeah.
And we can also pass, we already pass context, but we can make sure that we pass sufficient context into the back objects RPC, and we can decide in the back objects RPC, we're just going to run back objects for you and not look at the cache. So
so we could, like for the HTTP thing, like there's that thing where you can set config to set an extra header, for instance. Like we could use that. We could use like, you know, basically anything that we want like there.
Yeah. I think probably, I mean, if we want to validate this with CI, probably the easiest thing to do is a feature flag that is per project. Because otherwise you need to tell all these CI things to set the extra header and modify with their pre-clone script.
Well, we need to modify our pre-clone script anyway, because if our pre-clone script's happening, then we won't notice any effects of this as true. Much. But we could easily roll it out on like the website repo or like the Gitly repo or the omnibus repo instead, for instance.
Yeah. The minimal thing that should be there is a feature flag, and we can feature flag this per project, as far as I know, because we have to support. Nothing happens before this goes through Rails, and then in Rails we can say whether the feature flag goes on or not, and then that gets handed down to Gitly, and then here we can decide whether or not to add this config option.
Yeah, I think per project makes a lot of sense.
And on top of that, like you say, we can have all sorts of selection mechanisms. We can say there's a header, or we can say there's a config setting in Rails, like this project does or does not have it. And we could even, but this is harder, we could even analyze the list of objects that the client is asking at the moment we're in back objects and say, this looks like a request we want to cache, or this does not look like a request we want to cache, and then make a decision. But that's harder because then you need to, well, pretty soon you need to start running an ad hoc analysis on the Git repo and on the shape of its history to know what's going to happen.
So just out of curiosity, what does the object list look like for a shallow clone of the GitLab repo? Like, how long is that? Like, I think we had that in the output you were showing at the start, right?
No, I don't. So you mean what, the input to pack objects?
Oh yeah, sorry. Yeah, no, it wouldn't be that what you were showing at the start because it's the input, not the not the output. Yeah.
We considering this is a recording, and
yeah, this is an idle question. It's not essential for the demo.
We can, but if you want to play with this, just to make it clear, there is somewhere in here we cache the whole inputs into a temp file. Where is that? Here. So this is the list of objects, really. And it gets put into a temp file, and we delete that, so it's an anonymous temp file, so it's only visible to the Gitly process. But if you comment this out, or if you make this not a temp file, but some known file, then you can do one clone, and then afterwards look at that file in TMP and see what's in there.
Yep. Okay.
I could almost do that now while we're talking, but I don't think I should.
Yeah, no, that's fine. I was just curious because like I was like, well, that seems like, you know, like it already sounds like that list of objects for a shallow clone is going to be too big for us to be able to just like do a simple heuristic, and like you said, a more complicated one is going to involve, you know, much more work in terms of like analyzing the repo.
No, actually, not necessarily, because there are two ways of telling back objects what to do. One is a literal list of objects, and one is a list of commits you want and commits you don't want. And then back objects computes the full list of objects for you. So in that second case, the list isn't that long. And in the case of a shallow clone, it's actually very short. It just says, I want this commit, and I don't want anything below this commit. And then back objects just figures everything out on its own and never tells you what it picked.
Okay.
But
from here,
on the other hand, we don't control how back objects gets run, right? The Git itself creates the argument list and the inputs for back objects and make its own decisions about what to do. And the moment we start making assumptions, we are digging more into it. We're tying ourselves to a specific version of Git and the choices it makes and how it invokes back objects. And if we just have a thing that always caches, then we sort of can't do it wrong.
yeah, I think it makes a lot of sense to treat that input as opaque and just like,
yeah.
We don't care what the input is. We're just going to cache based on this input.
Yeah, exactly.
Okay,
because
so
this input just gets hashed. We compute the SHA-256 of whatever is in this file, and that's it.
So yeah, Rachel mentioned that the next steps we should do async because she had to join another call. Was there anything else you wanted to show us here?
No. Thanks for listening and thanks for your attention. I should stop the recording then. Where's the button for that?